we're going to continue with linear programming. We're going to look at some more scenarios. In our day one, we were given the X and Y, or excuse me, we were given the constraints, the inequalities, and the objective function. We're actually going to try and come up with those given a scenario, and then proceed to maximize or minimize depending on what we're asked. So in this one, don't ask me where this scenario came from, but supposedly Kate is a cargo pilot and she's transporting toenails and earwax. I don't know who Charlie is. A monster? Don't know. King Kong? Really have no idea. Anyways, toenails weigh 40 pounds and have a volume of 2 cubic feet per container. Earwax weighs 50 pounds and has a volume of 3 cubic feet per container. Kate charges $2.50 per toenail container and $3 per earwax container. Her plane can hold a maximum of 2,000 cubic feet and 37,000 pounds. Okay, so pretty much all of our scenarios, you guys, when we're dealing with word problems, are going to be positive values, because if we're answering this question, how many containers, we're not going to have negative. So almost always with these, we are going to have an inequality where X and Y are greater than or equal to 0. Now we do need to establish what are X and Y representing. That's where I want to go to this question. How many containers of each? So the types of containers I have are the earwax and the toenail container. So I need my variables to represent one of each of those. Doesn't matter which one we make what. I'm going to go ahead and make X be the toenail container and Y be the earwax container. And sorry, I should probably be more specific, the number of those. Okay. All right, so now I can specify, okay, for sure both of those, the number of containers have to be greater than or equal to 0, both the toenails and the earwax. Okay, but we have more constraints than that. So constraints, think about things that we're limited to. So for example, sorry, there we go. The plane is limited by the space and the weight it can hold. So space is volume. So there is a maximum volume that we can have within this cargo plane, okay? And that is 2,000 cubic feet. So each of the containers have their specific volume associated with it. Sorry, trying to clear there we go. So we want one inequality dealing with the volume constraint and one inequality dealing with the weight constraint. So I'm going to start with the volume. So the toenails have a volume of 2 cubic feet per container, so 2x, and the earwax containers have a volume of 3 cubic feet per container, and my maximum volume, so this amount, the volume for each toenail container and the volume for each earwax container must be less than or equal to the volume that the plane can hold, which is 2,000. Okay, so that is a constraint. I cannot go over that the 2,000 cubic feet. Now, the 37,000 is talking about weight in pounds, so I cannot exceed that. So now, the weight per container for toenails is 40 pounds, and for earwax is 50 pounds. And I must stay underneath that 37,000 pound constraint on the cargo. So now you might be asking, okay, well, there was something dealing with cost. We have nothing involving the prices here. That's actually where the objective function comes into play. We want to maximize profit. So kind of we were foreshadowing a little bit. We were using P for the objective function. That's because a lot of times these programming scenarios are looking at how to maximize money. So profit is the word for that. So we're going to use P again for profit. So this is where we're going to use the cost. So we want to know kind of what X and Y values must be to fit the constraints and maximize the profit. So this is where I'm going to use X and Y, and I'm going to use the cost for each. So it was $2.50 per toenail container and $3 for the earwax container. Okay, so that is our objective function. So we're going to follow, now that we've written the constraints and the objective function, now we are going to find our vertices, follow the same process as before. So I need to graph these. So no surprise, above the x-axis to the right of the y-axis so that we are positive. Oh, sorry, that was awful. Just trying to darken it so you can see it a little bit. Okay, so we know we're in quadrant 1. Okay, I'm going to use intercepts again. So if I plug in 0 for x, I'm doing 2,000 divided by 3, which is 666 and 2/3, and I plugged in 0 for x, so that is a y-intercept. Okay, I'm just kind of estimating on here where it's going to go. So 666 and 2/3 is an intercept there. Now if I plug in 0 for y, 2,000 divided by 2 is 1,000. Okay, so I'm going to put, and then connect. Okay, I'm going to test really quick a point. I'm just going to test 1 and 1. Easy enough. So if I put 1 in for each of those, I get 5, and 5 is definitely less than 2,000. So right now, I'm roughly looking at this triangle region. But now I have one more to add in here. So I'm plugging in 0, so I'm doing 37,000 divided by 50, which is 740. So that is a y-intercept. Okay, plug in 0 for y, so I'm doing 37,000 divided by 40, and I get 925. Okay, connect here. Okay, so now I need to know, is it this region right here? So I have this intersection point, so is it underneath all of those, or is it this little piece right there? So I'm going to test the point here. So I'm going to test like 950 and 1. Okay, so I'm testing this bottom one, and I need to know, is that going to be less than or equal to 37,000? Okay, so I'm going to plug in 950 for x, so 40 times 950. Sorry, I should write that. So I'm doing 40 times 950 plus 50 times 1. Sorry, 1 for y, and I'm asking, is that less than or equal to 37,000? Okay, so quick test. So I got that plus 50, and I am greater than that. So that means this part is not a solution. Okay, so it has to be underneath this whole one, which the overlap then is this part right here of all 4 of those. So not this little triangle region. And we could have also tested something in here too, you guys, 1, 1, and we would see that that would be less than, that probably would have been easier, sorry. Plug in 1, 1, that's less than or equal to 37,000, so that is definitely our solution set. So we actually have 4 vertices this time. I'm going to put them up here, you guys, vertices. So I have 0, 0. I have 0, oh sorry, I'll go up the y here first. So I have 0, 66, 666, and 2/3. Lots of repeating sixes there. 0, 740. Oh, what am I doing? Sorry, that's not one. I'm looking at the vertices that are bounded around our feasible region. So I got 1, 2, 3, 4. So this one's the other easy one to see. 925, 0. Now this one is one I'm going to have to solve for. So I'm going to do that down here. So that's the intersection between those bottom 2 inequalities. So I'm going to solve that system. So I've got 2x plus 3y equals 2,000, and 40x plus 50y equals 37,000. Okay, so I'm going to do elimination again here, you guys. I'm going to multiply everything here by negative 20 so that I get negative 40x. So I have negative 40x, and I'm just going to write that down here. Minus 60y, and let's see, I'm going to get 2,000 times negative 20, make sure I get enough zeros on there, is negative 40,000. Okay, so now I add, and I get x's to eliminate, so I get negative 10y equals negative 3,000. Okay, so then I get y is 300. Okay, so I know the the y coordinate of the intercept. Now I got to plug in y into one of these original functions. I'm just going to do the first one. So I have 2x plus 3 times, we just got 300 for y, equals 2,000. So I have 2x plus 900, 2,000. 2x equals 1,100. So x is 550. So that last vertex right there is 550, 300. So 550, 300. So that is my other vertex here, 550, 300. So now I need to know which one of those is going to maximize our profit. So now I'm going to use my objective function. So 0, 0, we are plugging in 0 for x, 0 for y, which is 0. Plug in 0, 2/3. So we have 2.5 times 0 again, which isn't going to give us anything. 3 times 2/3. So if I do 3 times, and I'm just going to add on a lot of 6s there. All right, so we get 2,000. All right, now we are plugging in 925. So 2.5 times 925 is 2,312.5. And our last one was the 550, 300. So we have 2.5 times 550 plus 3 times 300. Okay, so we got 2.5, 550 plus 3 times 300. So we get 275. Okay, so the maximum here is this one. Sorry, I should put a check mark. That looks more official. So this was the maximum amount. So how we would answer the question, how many containers should she transport to maximize her profits? Well, when I plugged in 925 for X and 0 for Y, that is what produced the maximum profit while staying within the constraints. So remember, X was toenail containers and Y was earwax containers. So Kate should carry 925 toenail containers and 0 earwax containers to maximize her profit, which the maximum profit she can get is that $2,312.50. So this would be the answer to that problem. Okay, these are long, so keep in mind, you guys, again, this homework is going to be pretty short, so because each of these problems are long, but I am going to do one more in this video. Okay, so in this one, we have, sorry, keeps clouding up on me. Curtis has a dog, Fifi, and wants to keep her diet varied. His vet recommends at least 30 grams of protein every day, at least 16 grams of fat every day, and no more than 12 ounces of food per day. There are 2 types of dog food, type A, which has a certain amount of fat and protein, and then type B, which has a different amount, and their costs are given there per ounce. How much of each type of dog food should Curtis mix together to meet the vet's requirements and minimize the costs? So here we're looking at a minimum. Okay, so the question is how much of each type of dog food? So that is what our variables are going to represent. So I'm going to let let X represent type A dog food. And I'm going to have Y represent type B dog food. Okay, so constraints. We're talking about types of dog food. How much, sorry, I should put maybe in grams because we're talking about amount, okay? Or actually, sorry, amount, not grams. We're not talking about weight. Let's do ounces. How many ounces, since everything is in terms of ounces? Okay, how many ounces of dog food? Okay, so here we need the constraints, and because we're talking about weight in ounces of dog food, again, we have the typical constraints must be greater than or equal to 0 for both types of dog food. Now, the other constraints we have is we had a maximum, or excuse me, we had at least 30 grams of protein. So that means it could be more than 30 grams of protein. Similar, we had 16 grams of fat, at least that amount per day. So I'm going to have a constraint with regards to the fat consumption and one with regards to the protein consumption. So I'm going to do fat first. So type A had, sorry, did I say, I forgot already what I said. Oh, we'll do protein first. Okay, so type A has 2 grams of protein. So 2x is 2 pounds per those ounces, okay? And type B had 6 grams of protein. Now, 6, but type B is Y for us. Now, at least means this could be more than 30 grams of protein. So I'm going to do greater than or equal to 30. So 30 is the minimum amount they want. More than that's great. We're doing something really similar with fat. So it's 4 grams of fat for type A, 2 grams of fat for type B. We want the fat consumption to be at least 16. Okay. I'm actually going to use C instead of P here for costs, because this one we're not talking about a profit. We're trying to minimize the amount of money spent on dog food. So the cost, I'm going to use C. So for type A, it's $2 per ounce. And for type B, it is $3 per ounce. So that is our objective function here. Okay, so start by graphing. All right, so we have our first one's greater than or equal to 0, so we know we're in quadrant 1. Okay, so I'm going to jump right into this one. So intercepts, plug in 0 for x, and I'm solving for y, I would get 5. So let's see if I can fit all these on here. I want 12. Okay, 1, 2, 3, 4, 5. Okay. If I plug in 0 for y, I would get 15 for x. Okay, so I might not be able to fit all this on 15, so I'm going to do 15 is there. Okay. Connect. All right, right now, if I were to plug in 1 and 1, this would not be greater than or equal to 30. So so far, I'm above this line. Okay. Okay, next one, do intercepts. So plug in 0 for x. I would get 8 for y. 6, 7, 8. There we go. And plug in 0 for, oh, shoot. Did I do that backward? No, we're good. Okay, plug in 0 for y, and I would get 4 for x. Okay, so now here. Okay, so now I have this like unbounded region, which is kind of a problem right now. Well, sorry, let me go back one more thing. So my options are in this little piece or here. So I'm going to pick an intercept just because that's easy to test. So I'm going to do 0, 6. So if I put in 0 and 6, I would get 2 times 6 is 12, which is not greater than 16. So that means I'm not in here and I'm currently above here. And I actually forgot one more constraint, you guys. We had a constraint on the amount of total food per day, no more than 12 ounces. So the total ounces of type A plus the total ounces of type B must not be over 12. Okay, so I have one more. So I have 12 and 12 when I plug in those zeros for intercepts. All right, so now I need to know, is a point in here a solution or here? And we are always going to have bounded regions in this one, you guys, so it's got to be in here so I actually have vertices. But we could always test a point again. I could test a point like 1 or 2, 9 or something like that. Or actually, let's test something like this. Let's test 0, 9. So if I test 0, 9, 0 plus 9 is less than or equal to 12, so it's got to be underneath, not above. Okay, so vertices, bounded region, we have 4. Okay, so I have 1, 2, 3, 4. I know these two, so I'm going to put vertices. Okay, so my vertices here right now I know are 0, 8 and 0, 12. Okay, so we're going to have to find these other two. Okay, so this one right here is the intersection of these two. So I'm going to solve that system. So I have 2x plus 6y equals 30. 4x plus 2y equals 16. I'm going to multiply the top by a -2, cancel my x's. So clear that up again for you guys, okay? And I'm just going to write it down here. So I've got -4x minus 12y equals -60. Add. So I get -10y equals, let's see, -44. So I get y is 4.4. Okay, we need to plug that back in here. So I'm going to get 2x plus 6 times 4.4 equals 30. Okay, if I solve that for x, I'm just going to do those steps on my calculator here, you guys. So I'm going to do 30 minus 6 times 4.4. And then I would have to divide by 2 to get x. So x is 1.8. So this point right here is 1.8, 4.4. So that is another vertice, 1.8, 4.4. Okay, we got one more to find, this one. So this one is the intersection of, I know I should like star these when this one is 12, 12. And this one is this one. There we go. There's a learning lesson kind of if you want to label them or draw lines so you know which one's which, that makes this part a little easier. Okay, so now I'm solving the system with these two. So I have, do it down here, 2x plus 6y equals 30. X plus y equals 12, and multiply the bottom one times -2. So I get -2x minus 2y equals -24. X's cancel. 4y equals 6. So y equals 1.5. And if I plug that one back in, I'm going to do the bottom one just because it's a little easier. So I got x plus 1.5 equals 12, so x would be 10.5. So this point then here is 10.5, comma 1.5. Okay, so now we are going to see which one of those vertices will minimize our objective function. All right, so testing 0, 8. So I have plus 3 times 8, 24. Test 0, 12. $36. Oh, I forgot my other vertices. Sorry, guys. I'll list that up here. 1.5, 10.5. There we go. Okay, testing 1.8 and 4.4. Okay, I'm going to do that one in here. So we have 2 times 1.8 plus 3 times 4.4. So we get 16.8. So far that's our minimum. One more to test. Test 1.5, 10.5. So we have 2 times 1.5 and 3 times 10.5. All right, so our minimum here, you guys, is that 16.8. So to answer the question, how much of each type of dog food should Curtis mix together? Curtis should mix. So remember the X was type A, Y was type B. So mix together 1.8 ounces of type A with 4.4 ounces of type B to minimize his cost of $16.80 if I turn that to a dollars and cents amount. All right, that is it for this video, guys. Thanks for hanging in there. More with linear programming to come. Thanks for watching.